In this tutorial, we will learn to import a DXF file as a layer into Trisco 2D and then learn some advanced tips and tricks. You can download the corresponding files from the link mentioned in the description. The benefit of Trisco 2D, unlike Trisco, is that you don't need to prepare the CAD drawing into separate layers with closed polylines representing each material. You can use any DXF drawing as an underlayer in Trisco 2D. Save the drawing in DXF format. Now open the Trisco 2D application. From the File menu, choose Import DXF and choose the DXF file. The CAD drawings units were in centimeters, hence we input units of the DXF file as 0.01 meters. You can see the total size of the drawing along the X and Y axis. You can select the layers you don't wish to import. In our case we wanted to import all, so we didn't choose any. Then we can choose to automatically create horizontal and vertical lines based on the DXF drawing. These grid lines can later help us to define the blocks. Upon clicking OK, we see that the DXF file has been underlaid with auto-generated grid lines. At Grids window, we see the grid extents along X and Y axes. In case we have not selected to create automatic grid lines, we should have drawn each of these grids individually. We see that there is only one block created with maximum grid extents along X and Y axis. This can clearly be noticed if we change the color from white to any other, for example, 15. You can change it back to white, color 0. Here the DXF drawing you see is just acting as an underlay helping us to create the blocks. Analysis is only performed for the created blocks. So, ensure that you create blocks representing the geometry using the underlay drawing as a reference. We will now try some intuitive techniques exclusively present for Trisco 2D. From the Colors menu, choose the list defined so that we see an entire list of predefined colors. This helps us to select colors and apply them to the drawing. Now we select the color we want to apply, say color 148 for medium density masonry wall. Now using the draw function, we can click on multiple grid cells to apply the color. As you click on grid cells, you see that blocks representing these colors are created where grid domains are automatically defined. We have briefly seen how to add a grid in the previous video using insert after. We shall now explore in detail various techniques to modify and add grids. At the image window, choose Set Horizontal Grid Lines icon and now you can click where you want to insert the grid. You see that the grid is created and parameters are automatically updated at the grid and block window to incorporate the new grid. So you can click on any location you want to add a horizontal grid. Similarly, you can click on Set Vertical Grid Line and click on the location you want to add the vertical grid. You can also snap grid lines to the underlay drawing as reference points. Now choose Move Grid Line and select the grid you want to move, drag and drop to the new location. During manipulation of the grid line, the new position is indicated in the status bar. If you drag the grid beyond its adjacent grid, the grid gets deleted. We now will define the remaining blocks. At Draw mode, now choose color 151 for insulation, then click on the grid cell. Now you can hold Shift and click on the last grid cell to fill all the intermediate cells along the line with the same color. To pick any color which is already applied to the drawing, right-click on the color at the image window, say brick masonry, and then apply to grid cells by left-clicking the outer fascia wall. Instead of medium density, you can also select color 180 for heavy density wall and apply to outer fascia. Select color 17 limestone and apply for coping stone. Color 32 for the bitumen sheet. Color 135 for roofing insulation. Color 72 concrete for the roof flooring bed. Color 136 reinforced concrete for roof slab. Color 190 for indoor upward heat flow. For boundary conditions, we choose the fill function. This would fill the color within the boundary of the grid cell and also fills the colors outside till the border of adjacent defined blocks. We chose color 174 and applied it to internal boundary conditions. Similarly, color 170 for external boundary conditions. Now from the Edit menu, choose Derived Thermal Properties. Here we choose Linear Thermal Transmittance. To evaluate the linear thermal transmittance psi value, the 2D heat flow is divided by the temperature difference and then subtracted by 1 du value of the wall, multiplied by the length of the flanking element of the wall. Then subtract with 1 du value of the roof, multiplied by the length of the flanking element. Flanking elements could be with external or internal dimensions as shown in this image. This choice is based on the respective national codes. We choose the external dimension for our example. Upon clicking OK, we notice two tabs where we can define these lengths of flanking elements and 1 du values. To define a distance, we need to define the coordinates of 2 points between which distance must be measured. Click on the first row to define the first flanking distance. Left-click on the first corner, then hold the mouse and move the cursor till the end point of distance. Similarly, you can define the length of the second flanking element, by clicking on the second row. Left-click on the starting point, then hold the mouse and move the cursor till the end point. We now notice both the flanking distances are defined. We now also need to define the 1 du value of the wall and roof. We shall define them at the borders of the geometry where there is a 1D heat transfer. To define the coordinates along which the 1 du value must be calculated, left-click on the first point and then hold the mouse by moving the cursor to the end point. We now automatically get 1 du value for the wall between these coordinates. Similarly, left-click on the first point and then hold the mouse by moving the cursor to the end point. Here the first row of the flanking element corresponds to first row of 1 du value. Now once we define the flanking element and 1 du values, we need to refine the grid to be suitable for analysis. In the previous videos, we have seen how to auto-split the grid. At Trisco 2D, upon clicking on Calculate System, the software automatically asks you if you want to split the grid. Choose Grid Base Size as 1 cm. Click on OK, then we notice the grid being split and calculation being performed. Upon completion, open the graphic output. We have already discussed various options present in graphic and text output. Choose Fill Temperature to visualize the temperature gradient. Now you can close the graphic output. Now click on Text Output. Here you see the derived thermal properties, which is the psi value. You also notice 2D heat transfer, 1 du values and lengths of flanking elements. You now can close the text output. You can save and close the Trisco 2D project. We shall see how to convert the Trisco 2D project into 3D at Trisco. Now, open Trisco. Then from the File menu, choose Import Data. Now from the Import window, choose Trisco 2D data file and select the file from its location. We set the plane along which the 2D geometry has to be placed. In our case, say XZ plane. Then we can choose the depth of extrusion. Say 1 meter. Upon clicking OK, you notice that the 2D geometry previously created in Trisco 2D has now been converted into 3D, where the grids, blocks and colors are automatically detected. You can watch Trisco tutorials to learn further about Trisco. The link is mentioned below. Thank you for watching. Hope you enjoyed using Trisco 2D.